Hello students, welcome back. Right now, our game is coming along great. We have our player movement, which follows the direction of our thruster alignment. That tracks our mouse movement on the screen. We can accelerate by firing our thrusters and move under proper physics motion with drift and drag. And we have a fuel system that we can manage ourselves for our player, that if we run out, we find ourselves in kind of a sticky spot, right? We could just drift off the screen. All of that is working wonderfully. But there's a glaring issue. And the glaring issue is that our game will run really, really fast on fast computers and really, really slow on slow computers. And that's because our game is currently frame based. If you remember, we talked about like how much fuel we would lose per frame of the game. Well, on some computers, they might run 60 frames in a given second. And on other computers, they might only run 30 frames in a given second. This is going to cause inconsistencies in our gameplay, and those inconsistencies are extremely bad. We want consistent feel, consistent play across any machine, no matter how slow or fast, old or new. And so what we're going to do in this video is we're going to take our frame-based gameplay system and convert it into a time-based system, because no matter the computer, time is the same. 1 second is 1 second is 1 second, whether it's on a slow computer, a fast computer, or a computer that falls somewhere in the middle. Once we develop this new time-based system, we'll use this system to scale our difficulty by creating something known as a ramp. A ramp will be a mechanism with which we can control how hard our game is, and it will increase gradually and smoothly the longer we play our game. So some things that we might be able to control via a ramp are the potential asteroid systems that we're going to bring in. How often will we spawn an asteroid, and how fast might they move when they're on the screen? So let's head over to the computer screen and let's dive right into this lesson on all about time and ramps. So I have lesson 5 starter file open right here, delta time and our difficulty ramp. I'm going to minimize this file here and I will open that file directly in the browser. So we'll go to our folder and we'll open up lesson 5. And so let's look at what we got here. Right away, I see I got this data collection time, 0 seconds, so I haven't collected any. Whoa. And my probe zoomed off the screen. I don't know if you guys saw it, like I fired it out of a cannon. Ready? I hit space, and all of a sudden my fuel completely depletes, and I'm gone right there. I'm out of there. So it looks like we have switched. We're trying to switch from a frame-based system to a time-based system, right? But some of the things that required maybe frame-based movement are broken. Like our player movement system is broken. Our fuel system is broken. Those are things that we were really leveraging frame-based movement prior, and now we're switching over to time-based movement. So we got to adapt and adjust all of our systems. And I'd really love to see this timer actually working. So let's head over to lesson 5 and let's see what we got. Number 1, it says adjust the delta time variable. All right, so we're gonna head to lesson 1, but before we do, let's just go look at what happened to our gameplay constants, because some of these things have changed. So if you look here, like our thrust acceleration value has changed. It used to be 0.017. And that was back when we were talking about a frame-based system. But now we are moving into a time-based system. And so what we're going to do here is acceleration is essentially like pixels per frame squared. So frame squared. So if I'm running at 60 frames per second, what I need to do is take that 0.017, which was our original acceleration, 0.017, and I'm going to multiply by 60 frames per second, and then I will multiply by 60 frames per second again. Why am I doing it twice? Because acceleration is typically frames squared in the denominator, all right? And so this is going to give me pixels per second squared. So I'm going to change that value to 61.2 pixels per second squared. And you can see we did something similar down here to our fuel cost. Our fuel cost was 0.083 fuel units every single frame. So 0.083 fuel units every single frame. If I multiply that by 60 frames per second, assuming, I get roughly 5 fuel units per second. We've also changed our drag value to be time-based as well. And so now I have it at 0.08. And the way I do that is by taking the natural log of the value that we had before and multiplying it by our 60 frames per second. Okay, so those numbers have all been converted, but I don't think the systems, our update systems, are maybe showing that. We also have some variables here for this ramp that we defined, this thing that was going to control how difficult our game is going to be as we increase. And we can see we have some things that we're going to control, like our asteroid speed at the start and at the end of the game, and our asteroids per spawn when we start and end. And then we also got this thing called ramp time seconds, which we'll talk about. But I want to get some familiarity with what these variables are before we dive into mission number 1. So now let's take a look at mission number 1. It puts us right here in the draw function. And so the first thing that we're going to do is we're going to talk about this new variable called delta time. Delta time is a built-in variable that measures the number of milliseconds that have occurred since the last frame was processed. All right, so how many milliseconds has happened since the last frame? Now, we want to convert milliseconds into seconds. We don't like working with milliseconds. And so there are 1,000 milliseconds in a given second. So to convert here, we just divide by 1,000. Now, what we're going to do is we're going to use this to determine how much time has elapsed from the last frame, and then we'll convert that into seconds. And we're going to store it in a variable called dt for delta time. Now, right now, it is set to 1. So 1 second has not elapsed since our last frame. If it was, then we were running our game at 1 FPS, 1 frame per second. That would be really, really bad. So what we're going to do is we're going to take this variable called delta time, which is the amount of time that has passed since the last frame in milliseconds. And to convert it into seconds, I will divide by 1,000. Awesome. So this is pretty good. So, right, so whatever delta time is, we divide by 1,000, boom, we got our dt. And now we're going to use this dt to control our game, our time interval, because if dt is, say, like a tenth of a second is a tenth of a second is a tenth of a second, no matter what computer we're on, a fast computer, a slow computer, a computer right in the middle. There's only one problem. This delta time here, the time elapsed since our last frame was processed, could potentially vary. Like if I'm playing my game, and then I go off this tab, and then I come back to it, that DT value could spike. It could be huge. Imagine if I was over here for like, I don't know, like 40 seconds doing something, and then I came back to my tab. Well, then DT would be like 40 seconds. That's astronomically huge. And that could cause some really wacky gameplay if we had a DT value that was that big. So I want to sort of set a maximum number that we will allow for DT. Now, this is a little confusing. This always confuses me. If I want to set a maximum number that we will use for this DT variable, what I can do is use the min function. So the min function is going to pick the smaller of two values that I give it. So I'm going to give it, I'm going to set a lower bound of 0.033, and then my upper bound will be delta time divided by 1,000. So let's just look at an example here. Like let's just say, oh, I don't know, delta time, the number of milliseconds that has elapsed. Let's just say like 2 milliseconds or 2,000 milliseconds have elapsed, which is 2 whole seconds. So I'm playing my game, I go off, and then I come back. So 2 whole seconds have elapsed since I'm playing. So 2,000 divided by 1,000 gives me 2. So basically, dt would become 2. That could spike our gameplay. So what we're doing is with the min function, we're saying, okay, between 0.033 and 2, pick the smaller value. So we pick 0.033. So there we go. And what if we were away for like, if we were away for like 1 whole second, like 1,000 milliseconds? Well, 1,000 divided by 1,000 is 1. So pick the smallest of 0.033 or 1. We would pick 0.033. So this is like our guaranteed upper bound. But what if we were away for, oh, I don't know, like say 0.005 milliseconds. I divide by 1,000. Well, now that's smaller, so we would take that. Okay, so that's how we're going to get our time interval, and it's going to be consistent to prevent jumps and lag spikes. Mission number 1 in the book. Now we're going to use that DT in mission number 2. Look at we're right here. So it says runtime timer. Update the runtime variable using our delta time. Pass DT into the update functions that require time-based behavior. So it looks like we have a new variable to work with here called runtime seconds. I'm going to go check out our gameplay variables. Let's just see what we got here. In our gameplay variables, outside of our student edit zone, we've got runtime seconds. Okay, so that's initialized to 0. I'm thinking that's probably going to be that timer right there. And then we have a ramp variable, our asteroid speed variable, and our asteroids per spawn variable. So we don't have any asteroids yet, but we're laying the foundation to bring them into our game, and it's going to work really, really nice. So right now we're prepping. We're doing the prep work. But we've got this runtime seconds variable. Let's actually add to it. So right now we're adding 0 to it, which that's not right. I don't know. What do we want to add? Let's add 1. So let's add 1 to our runtime seconds, and let's see what happens. So I hit enter, and whoa, that's going pretty quick. I don't think we've been collecting data for 400 seconds right now, or 500 seconds, or 600 seconds. So this is not right. That is not accurate time. In fact, what are we doing? Well, we're inside the draw function, and remember, the draw function runs every single frame. So every single frame of our game, I'm adding 1 to runtime seconds. This is not showing the amount of time that has elapsed. This is showing how many frames we have actually processed. So that's actually kind of neat, right? Every single frame, we're adding 1 to this. So right now, my game has gone through about 1,500 frames. So but I mean, it's cool, but it's not what we want. I want to show the amount of time that has elapsed since playing the game. And so if you think about it, DT is going to give me the number of seconds that has elapsed every single frame. Delta time gives us it in milliseconds, and then we convert it, and we make sure that we clamp it for larger values. So why don't we add that DT variable right here? Doing that, making this plus equals DT, now when I run the game, I should have an accurate representation of how long the game has been played for. This is awesome. So right now, I'm certain 7 seconds is the correct value. And that 7 seconds is going to be 7 seconds on a slow computer, a fast computer, or a computer right in the middle. So pretty cool. Now there's a second part here. It says pass DT into the update functions that require time-based behavior. So some of these things might need to know about our DT variable. So right now this DT variable is only defined inside of this draw function. Think of it as it's like locked inside of here. And if it wants to go to another function, we have to sort of send it to another function by putting it inside of these parentheses. So let's go look at what might need to have access to our delta time variable. Well, let's see. We've got a new function called update ramp values. It looks like we got some missions in there we'll work with. Update thruster direction. I don't think that needs DT, but look at this. Update thrusters. It shows right here that it needs delta time. So we need that time to adjust our movement. That's why our movement system is so broken. When I hit the space bar, I just zoom off the screen because we're not using DT correctly in here. Same with our drift function. Okay, so update drift also needs it. So we need it for update thrusters. We need it for update drift. Check if player lost in space. I don't think we need it there. So we need update. Yep, we need update thrusters and update drift. So let's add it in here. So mission 2, we're going to pass in DT to update thrusters, DT, and update drift, DT. And with that, mission number 2 is complete. So let's move on to mission number 3. Where's mission 3 place us? It places us into update thrusters. I now know that this mission needs to have reference to that delta time variable, and we are giving it. We just passed it in. So now we have access to DT. How do we use it? Well, if we think about it, velocity, right? We're updating our velocity. We're saying it's just sort of being changed by acceleration. Well, that's sort of true, but there's another layer here, and we're just going to talk about a general form for acceleration. So I'm going to say that acceleration is essentially velocity divided by time. It's a change in velocity with respect to time. So if I want to solve for velocity, I got to multiply both sides by time. So time cancels, and what I see is an object's velocity can be found by looking at our acceleration and multiplying by our time. And we're just going to go one step further here because this acceleration actually has 2 parts. Boop, boop. It has a direction and it has a size. And if you look here, our velocity is equal, this is the direction of the acceleration, and this is the size of our acceleration. Our size is 61.2, and our direction is given by the direction of our thruster. So what we're missing here is our time. We're missing multiplying by time. What is our time that we're going to multiply by? Well, it is the time that has elapsed since our last frame, and that is our dt variable. So we're going to come over here, and we're going to say, all right, let's do, times dt times dt. Oh, and look, our fuel is already being adjusted for it. So we're subtracting our fuel cost per second, and then we're multiplying by our time interval, dt. So that actually is already working for us. So let's now see if we adjust our thrusters correctly, will we be better? All right, so our movement's still wonky. We're still not right, but our fuel system is now correct. So this is working much better. So we are adjusting the correct amount of fuel here. Very, very good. Okay, so now how do we fix our movement? Let's go take a look at it. I think that's probably going to be mission number 4. Mission 4, it's, yeah, good. It puts us in our update drift function because we are way off here. If we look, we have our player's position, and we're just setting it equal to our player's velocity. All right, so we got to go back to our whiteboard here because just like we had this relationship that acceleration is a change in velocity with respect to time, we could do something similar in regards to velocity and position. I could say, okay, an object's velocity is essentially its change in position with respect to time. And so I can multiply both sides by t. And when I do that, I get the distance of the player, or the position of the player, is their velocity times their time. We've already got the velocity, so what are we missing? We're missing our time interval. And that time interval is going to be delta time, our dt that we converted into seconds. So right here, I take that velocity. That's how fast we're moving in a given unit of time. I need to multiply by the given unit of time. So I'm going to multiply both lines by dt. And doing that, we should fix our movement. Let's check it out. So now our thrust system's working again. Our movement system is working again. Our movement system is not working. Oh my goodness gracious. It's almost as if my drag is just way too much. I'm slowing down like crazy. And that's probably why, because if we look here, we didn't apply dt to our drag. See, we've got drag per second. We converted this to a time-based system. So if that's how much drag we're given in a second, we need to know what our time interval is. So I'm going to multiply by dt. I'm going to multiply by dt, whatever our time interval is, right? If in 1 second, if the drag constant should be 0.08, well, I don't have a whole second of time. I have a much smaller value of that. And so now we are set. And so now if I look, I'm moving, I'm drifting, I'm accelerating, exactly the way I want it to. So this may feel exactly like we had it at the end of our last lesson, but it's much better because now if we were to play this on any given computer, the experience would be consistent. And I'm off the screen. Darn, I died. All right, so now with our time set here, let's look at mission number 5. Mission number 5 says we are going to add the ramp constants. So we said once we defined time and we had time, we were going to scale the difficulty of our game the longer we played our game. So as time goes on, our game should get more and more difficult. So this ramp system, we'll start by defining constants for the ramp system. So first we have this variable called ramp time seconds. This is the amount of time it will take for our game to reach its maximum difficulty. All right, so we'll start at the beginning, it'll be easy, and by the time we hit this number, it will reach maximum difficulty. We don't want that to happen in 1 second. That would be way too quick. I'm going to make it 120 seconds. So after 120 seconds, our game will be as hard as it is going to get. Now, what are we scaling in terms of difficulty? Well, I'm going to scale the asteroid's speed. So at the start of our game, our asteroids are going to be moving somewhat slow with a speed of like 50. By the end of the game, they're going to be moving much faster. I'll say 320. All right, so that's something that we're going to scale with our difficulty ramp. And another thing we're going to scale is how many asteroids we spawn or create when it's time to create asteroids. In the beginning, I'm just going to create one single asteroid at a time. But by the end of the game, I'm going to be creating 4 asteroids at a time. So now the question is, how do we go from this beginning value to this ending value? How do we go from this beginning value to this ending value in the 120 seconds of time? Well, hopefully, let's go to mission 6 and see if we can figure this out. Mission 6 brings us into a brand new function called update ramp values. It says create a ramp value based on runtime. Normalize it between 0 and 1 over time. So the first thing we'll note here is this update ramp values is getting called every single frame of our game. In our draw function, we calculate DT, and if we are in play mode, we update our runtime second timer. So this timer gets adjusted, and then we call update ramp values. This function is going to control the difficulties of our game. So the first thing it says, we need to create a ramp value based on runtime. So let's talk about how this is all going to work. I'm going to come over to the whiteboard right here. I'll make this full screen so we can see it nicely. And let's take asteroid speed as example. So a ramp is essentially a value between 0 and 1, okay? So it's somewhere between 0 and 1. So maybe it's like 0, maybe it's 0.33, maybe it's 0.86, or maybe it's 0.99, something like that, okay? And essentially what we're going to do is let's create a graph, zoop, zoop, and on the x-axis, we're going to put our low and high values of our ramp. So right here, we start at 0. And over here, we're going to end at 1. So there's our ramp values. On the y-axis, we are going to put values we want to control with our ramp. So for example, maybe I'll put the asteroid speed. So I think, what did we say we started it at? It was 50. And then we ended, our max asteroid speed was 320. So I know that at the beginning of our game, when our ramp is 0, so this is our start, the asteroid speed is going to be 50. When our ramp is 1, this is when we are at max difficulty. At max difficulty, what is our asteroid speed going to be? It's going to be 320. That's what we specified right here. Now, we have our starting point and our ending point. Imagine if we were to draw a line between this starting point and this ending point. Zoop. Our ramp value, if our ramp value were, say, 0.5, well, then we would go up to this line and we could read across as to what our asteroid speed might need to be. And I have no idea what's the in between here. But I'll guess, I'll just say like 200. All right. And if we increase our ramp and make it a little bit bigger, let's just say like maybe over here, 0.85. We could go up and read our value right off of this line. So maybe it would be like 290. And if our ramp value was smaller, if it was only here, if it was like 0.2, we could say, okay, what's our ramp value? What's our asteroid speed going to be? Maybe it's only 80, 85. So this process of taking the starting and ending value, drawing a line between them, and then using a ramp that is between 0 and 1 is known as linear interpolation. Or LERP. Okay, so we're going to talk about the LERP function, and we're going to use it to essentially figure out what value our variables need to be for our asteroid speed and for the number of asteroids that we're going to spawn based off of this ramp. Now, how do we get these ramp numbers? Well, at the max difficulty, this is going to be, what did we say, 120 seconds of gameplay. And so we have our runtime, right? Run time seconds divided by the max, what do we call it? Max ramp time. If we look at that ratio, that is going to give us our ramp values between 0 and 1. So let's take this idea of linear interpolation and let's head back over to our code and apply it now. So we want to create our ramp. So I'm going to update that variable that we had looked at called ramp. Remember, we defined it here in our gameplay variable section, right? It's right here, ramp. It was equal to 0. So now we are going to update it. So I'm going to say ramp is equal to run time seconds divided by ramp time seconds. So runtime seconds when we start the game is 0. Ramp time seconds is 120. So let's just see, what's 0 divided by 120? Well, 0 divided by 120 is, no surprise there, it's 0. That's going to pin us right at the start of our ramp. So for asteroid speed, our asteroid speed would be 50. So that's not too bad. Okay, our asteroid speed would be 50. So let's say the game goes on. So now we've played the game and we've played for 20 seconds. So 20 divided by our ramp time, which was 120, is 0.16. So now we're at 0.16 on a ramp. So we'd be like right here. So maybe our asteroid's speed would be, what, maybe like I'd say like 78 we'll say. All right, we play the game a little bit more. And so now we've played for 60 seconds. So now runtime divided by ramp time is going to be 0.5. So now the asteroid speed is moving faster at 200. Awesome. So this is working really nice. And we played the full 120 seconds. So now 120 divided by 120 is 1. We are at our maximum difficulty, and our asteroids are moving at 320 units. Okay. But there's only one problem here. If we don't die right then, runtime seconds is going to be greater than ramp time seconds. Runtime seconds could be like 140 seconds divided by 120. And if you look, that would be 1.16. I don't have a 1.16 on my x-axis. The idea behind the ramp is that it's got to be between 0 and 1. So we somehow have to limit it right here because this is supposed to be our maximum difficulty. The game should not get any harder. So what we're going to do is we are going to actually call the constrain function, and we're going to constrain that value of runtime seconds divided by ramp time seconds, and we're going to provide a lower bound of 0 and an upper bound of 1. We now have our ramp. Excellent. So let's use that ramp now. I don't think that's going to do anything because we're not doing anything with the ramp yet. So let's use the ramp to control some things. If you look here, we're using the ramp to update the asteroid's speed already. And we're doing it through this process of linear interpolation, or LIRP. We're specifying the starting value of 50 and the ending value of 320, and then we're specifying where on that ramp we want to be. Okay, so that ramp could be between 0 and 1. So if the ramp were 0.85, bloop, it puts us right there and we get our value. We need to do something similar for our asteroid spawn. So how many asteroids are we going to create per spawn? So I had a variable for this. I think it was asteroids per spawn. And I'm going to update its value using linear interpolation. I have to provide the lower value. So I'm going to do asteroids per spawn start, which is my second one here. And then the final value is going to be asteroids per spawn end. And then that defines the starting point and the ending point. So we're getting like a ramp that looks what, like this. Let's just make sure we fully understand this. My ramp is going to look something like zoop, 0 to 1. And when we start, we had 1 asteroid spawning. When we end, we had 4 asteroids spawning. So that's what it's going to look like. All right. So we have that. We're going to put this in and we're going to put ramp here. So not too bad. So as time goes on, we're going to move further and further along this ramp and spawn more and more asteroids. There's just one big problem here. If we look here, if I were like, oh, I don't know, at a ramp of say like 0.25, I'll say, boop, boop, boop. I come up here, boop, boop, boop. I don't know what this is going to give me. Well, let's not make it 0.25. Let's make it like 0.29. Okay. Maybe this is going to give me like, I got to spawn, oh, I don't know, like 1.87 asteroids. I have no idea. Okay. Here's the bad thing. We can't spawn 0.87 asteroids. That's not possible. When you spawn an asteroid, you can spawn 1, 2, 3, or 4 asteroids. They have to be whole numbers. So if we were told to spawn 1.87 asteroids, that's going to be pretty bad for us. So we're going to actually round that number. So whatever we get from the LIRP function, we are going to round it. And all we got to do that is we just call in front of LIRP, round. I'll open a parentheses, and the thing that I want to round is the entire result of my LIRPing, my linear interpolation. So all of that needs to go inside of your round function. Hey, mission number 7 is done. Of course, we don't, it's unfortunate. We have no asteroids here to actually see the increase in speed or in spawn number. So how do I know my ramp is actually working? Well, what we're going to do is we're going to head to mission number 8. I believe we have a little bit of a debug here. Mission number 8 puts us in our draw HUD function right here. Perfect. And it says draw a ramp readout. Display ramp difficulty values in the HUD. Show progression clearly to the player. So I'm going to scroll down just a little bit. We got our draw fuel bar function. function. And then there's this nice debug function called draw ramp readout, where we show a bunch of text in regards to the ramp. We show the ramp's percentage, what the asteroid speed should be, and what the asteroids per spawn should be. So this function just needs to get called. It's like a debug function. So inside draw HUD, I'll call draw ramp readout. There it is. 2 parentheses to call it and a semicolon. Now that I call this, I have a debug way to see what my ramp values are. And there they are. They show up. What the ramp percentage is, what the speed should be, and how many asteroids we should be spawning. So let's press enter, and you can see time's going up. My ramp percentage is going up. The speed of the asteroid is going up. And the number of asteroids per spawn, well, let's see what we're going to get. All right. We're about 11% of the way there. Our ramp is looking pretty good. Our asteroids would be moving faster and faster and faster. And now we get 2 asteroids per spawn. Now, I don't want to wait all the way to the end here. So what I'm going to do is I'm going to go up to, let's go up to my constants for the ramp. Let's just change this to ramp time seconds to like 20 seconds. So now we'll reach maximum difficulty in 20 seconds instead of 4. Look at how quick the ramp is moving. All right. So in 20 seconds, so when we hit 10 seconds, we should be at 50% the way of our ramp. And we are, okay. Our asteroid speed's increasing. Our spawn, we're spawning 3 asteroids. And by the time we get to 20 seconds, there we are. We're spawning 4. See, and it's because we're rounding up. We hit 3.5, and now we're rounding up. Now our ramp's at 100%. We're at our maximum difficulty of our game. So this is really, really good. Not only did we switch to a DT system, so the gameplay is going to be consistent on slow computers, fast computers, all of those things, but we have laid the foundation for a ramp which will smoothly increase the difficulty of our game using asteroids. All we need to do is now add that asteroid system, and we can apply this ramp that we have created. I'm going to set this ramp time seconds back to 120 seconds so that it is correct and accurate, and I will make sure to save the game. All right, I think this is a wonderful place to stop. Like we said, our gameplay is now going to be consistent across all computers. That's extremely important. I typically like to start in the simple case, frame-based, and then when we are ready to, we transition to that time-based system, because doing so gives us the ability to create a difficulty ramp, something that will scale our difficulty smoothly with time the longer we play through that process known as linear interpolation. In our next video, we'll work on our pressure system of actually adding our asteroids, and we'll just plop them right onto the ramp, and the ramp will take care of scaling their speed and the number that spawn to make our game very exciting. So I can't wait to see you in the next video.